Hi, everyone. So I'm going to talk about the paper, an efficient reduction of a gammoid to a partition matroid. So a gammoid is a special case of a matroid, and it's a very complicated matroid. And what this work is going to be about is how to take a gammoid and, in some sense, convert it into a partition matroid, a matroid with much simpler combinatorial structure. And so this paper is joint work with Marilena Leichter, who's at the Technical University of Munich, Kirk Pruhs, who's at the University of Pittsburgh, and I'm Ben Moseley, and I'm at Carnegie Mellon University in the Tepper School of Business. And also, Kirk and I both consulted at the company Relational AI. So first, let me define what a gammoid is. So a gammoid is a special case of a matroid, and it's a matroid that corresponds to a directed graph. And in particular, it's going to correspond to feasible flows in some directed graph. So that is here, we're given some matroid M. And so here in this matroid, we'll let S be the collection of elements, and I is a collection of subsets of the elements. And so these collection of subsets we're going to call independent sets. Now the matroid M is going to be a gammoid when there exists a corresponding directed graph D, which we can represent over here. And now in this directed graph, there's a special node T, which is our sink. Now, critically, if you give me a collection of elements from the gammoid, this collection of elements corresponds to a set in I if and only if there exists I vertex disjoint paths from these vertices to T. And so that is a collection of elements is going to be independent in the gammoid if that collection of elements can construct vertex disjoint paths to T. And of course, these vertex disjoint paths can depend on which collection of elements that we're considering. So for example, consider some set I here, so some collection of elements of our gammoid, and so say they correspond to these three vertices here. Well, then these three vertices indeed are going to be independent because we can find vertex disjoint paths from them to the sink T. For example, we have three paths here from these vertices to T, and so therefore these guys are independent. Now, to describe our reduction to a partition matroid, this is going to be useful for colorings of gammoids and more generally colorings of matroids. So let me also define what a coloring of a gammoid is. So we're going to say that some given gammoid M is K colorable if we can take the ground set of elements and partition it into K sets such that each of these sets are independent and an I. So in other words, a matroid is K colorable if we can find a collection of K sets that in I where every element appears in one of these sets. So to see what a coloring corresponds to, let's look at the following example. So imagine that each of these vertices over here that are colored correspond to the elements of the gammoid. And so that is all of the elements of the gammoid are colored here. And so any of these nodes here that are black, let's assume that they are just dummy nodes in the graph and they do not correspond to elements in the gammoid. Now, this here is going to be a coloring of our gammoid. So we have three different colors. We have the green color, we have the red color, and then we have the blue color. Okay, and so this is a partition of the elements in different color classes. And now what do we need to show? Well, what we need to show is that each of these color classes corresponds to independent sets in the gammoid. And they indeed do. Let's consider the following. So first, let's look at the blue guys. So we have these three blue nodes here. And so these are going to be independent if they each can construct vertex disjoint paths to the sink T. And so we see that this can be constructed as follows. And so indeed, these blue guys correspond to an independent set in the gammoid. Similarly, we can look at, say, the green set. So now we have our green vertices here. And now these are going to be independent if they have disjoint paths to the sink. And then we can construct these as follows. And then finally, we have our red set. Now we look at the red vertices here, and now these will be feasible if we can find vertex disjoint paths. And indeed, they're feasible. Here are the vertex disjoint paths. Good. And so then overall, what have we done? Well, we've partitioned the elements of our gammoid into different sets such that each of those sets is independent in the matroid. Now, what's interesting is that matroid coloring is in P. And so that is, if you wanted to find the minimum K such that a given matroid is K colorable, well then in fact you can do this. So we can find that minimum K optimally in polynomial time. So the way you're going to do this is the following. You use Edmonds matroid intersection algorithm. So that is the algorithm that finds the maximum size independent set in the intersection of two matroids. And the way you do it is the following. Now, I'm not going to give the full reduction, but just an overview. So you take as input a matroid. It doesn't have to be a gammoid. It could be any matroid. You have as input a matroid. And now you also guess the minimum number of colors K, right? There's only polynomial in many of them. So you just fix one of these colors. And now you want to check if the matroid is K colorable. Now what do? Well, from your matroid and K, you construct two new matroids. So one is going to look like the original matroid, and the other is going to be like a partition matroid. And then you ask, what's the maximum size independent set in these two matroids? And what's going to happen is if the matroid, the original matroid was K colorable, then the maximum independent set in the intersection of these two matroids is going to correspond to that K coloring. Okay, so now, what are we interested in our work? Well, what we're interested in is reducing a gammoid to a partition matroid. Okay, and so what exactly do I mean by this? So to understand what I mean, first, let me define what a partition matroid is. So a partition matroid, it's a special kind of matroid. And here in a partition matroid, you're given a ground set of elements S and then a collection of independent sets I prime. So these again are just subsets of S that are independent. And these independent sets have a special structure. So in particular, there's going to be given in a partition matroid a collection of partitions of the ground set of elements. So as part of input to a partition matroid, you're given, say, a collection of R different sets for some parameter R. And now every element in the universe appears in one of these sets. And now a set is going to be in the collection of independent sets, so in I prime, if and only if this set intersects each of these given partitions by at most one element. Or in other words, as a part of a partition matroid, you're given a collection of partitions, good, and now you're allowed to select one element at most from each partition for a set to be independent in the partition matroid. All right, good. So now what do we want to do? Well, what we want to do is we want to reduce a gammoid to a partition matroid. So intuitively, we want to take the complicated combinatorial structure of a gammoid and somehow simplify that combinatorial structure so that it acts like a partition matroid. Now, what do I mean by this? Well, what I mean by this is the following. So you're given your gammoid as input on some ground set of elements S and your collection of independent sets I. Then from that, you're going to construct some partition matroid on the same ground set of elements S, and then a collection of independent sets over here that correspond to the partition properties that we just discussed. And now, what we want is the following property. So let's consider any set I that's independent in the partition matroid that we construct. Then it should be the case that this independent set is also independent in the gammoid. And so that is, we take our gammoid as input, we convert it to our construct on the side, some partition matroid. And now, if a set is independent in our partition matroid, then it must be the case that I is independent in the gammoid. So that's our goal, is to take our gammoid and make such a partition matroid. Now, if you think about this for just a minute, what you're going to realize is that this is an extremely easy thing to do. Okay? So For instance, what we could do is just make our partition of the partition matroid be the entire ground set of elements. That's a perfectly reasonable partition matroid. What it says is a set is independent if you only pick one element, right? No problem, that's a partition matroid. And then if we only pick one element, clearly picking one element is feasible over in our Gammoid, and so then we're done. Okay, so this ideally, this isn't really what we ideally want, so we want something stronger than this. So the stronger thing that we want is we want to somehow keep the same combinatorial structure after we do the reduction to the partition matroid. And so what exactly do I mean by that? Well, the idea is the following. So let's say that our original Gammoid was K colorable. Okay, and so you can color this Gammoid with K colors. Then what we want is that when we construct our partition matroid, the number of colors needed to cover this partition matroid doesn't increase by too much. So it's not very hard to see that for our partition matroid, the number of colors has to increase because any set that's independent in the partition matroid is also independent in the Gammoid, right? Now the thing is, we just don't want it to increase by too much. So ideally, we want a partition matroid that's as close to K colorable as possible. So some function of K colorable. So in fact, there has been some recent work on this problem. So Birksey et al. In 2020 gave a constructive exponential time algorithm to do this exact reduction. So that is, they can take in any Gammoid and they will construct a partition matroid such that if the original Gammoid was K colorable, then the partition matroid is 2K minus 2 colorable. And in fact, they show that this is the best possible. And so that is, there exists a Gammoid where if you're going to construct a corresponding partition matroid, then any feasible partition matroid, you're going to need at least 2K minus 2 colors to color that partition matroid. So they're basically the best possible. It's a constructive result. However, it's going to use exponential time. So the clear open question from this work was, could we do this in polynomial time? Now, at the same point in time, Im et al. In 2020 showed a similar result to this partition reduction. And so I'm not going to get into the exact definition here, but they showed something like a partition reduction. So you would take a K colorable Gammoid and you reduce it to something like a partition matroid where you can, it's similar to being, say, only O of K colorable. Now, additionally, Im et al. And Birksey et al. Independently discovered this idea of a partition reduction. And so a partition reduction can be used for any kind of matroid. So that is, you could take any matroid that's K colorable and ask, could you reduce it to a partition matroid that's only some function of K colorable? And now in their works, they show that this is possible for simpler matroids in the Gammoid. And so in particular, they show it for the cases of, say, a laminar matroid or transversal matroid or a paving matroid. And so for these, they can construct this reduction in polynomial time such that they increase the number of colors by some small constant factor times K. So what we show in our work is a constructive way to give a 2K minus 2 colorable partition matroid. And so that is, given any Gammoid that's K colorable, we give a constructive algorithm to give back a partition matroid such that the partition matroid is 2K minus 2 colorable, and any independent set in the partition matroid is independent in the original matroid. So now, given the result of Birksey that shows that you're going to need at least 2K minus 2 colors in the worst case, our result is tight. So we give an efficient polynomial time algorithm, giving us the best result we could hope for in terms of these partition reductions. Okay, great. So now we know our main theorem. So at this point, what I would like to discuss is a key application of our theorem. And so the application of our theorem corresponds to set cover on the intersection of matroids. And so what do I mean by this? Let me define this. So consider the general set cover problem, right? So in set cover, you're given a collection of elements and a collection of sets. And now what do you need to do? Well, you need to find the minimum number of sets, right, such that you cover all of the elements. So that is, you want to pick a collection of sets whose union of these sets equals the universe of elements, and you want to use the minimum number of sets possible. Now, of course, for the set cover problem, we know that there is a log n approximation for this problem. So the simple greedy algorithm gives us a log n, where n is the number of elements in the universe. And this is the best possible algorithm you can hope for. And roughly speaking, there's relatively few special cases where we can improve upon this log n approximation. So what special cases are there? Well, some special cases where we can improve on this are, say, for geometric problems. So if the sets correspond to geometric objects and our points correspond to points in Euclidean space, then we can get better results. The only other special case that I'm aware of is when we restrict, say, the size of the sets in some way. And so besides this is really the main two cases where we can go beyond this log n approximation. And it's really of interest to the community to say, improve upon this log n approximation for some special cases. So in fact, we can improve upon the log n approximation for some special cases. And in fact, we can do this when our set cover instance corresponds to the intersection of L gammoids. And so what do I mean by this? So imagine you have some universe of elements. And now I define a collection of L different gammoids on this collection of elements. Right? So I have L different gammoids here, each with their own graphs and their own collection of independent sets. Now, let's say we take the intersection of these gammoids. And by intersection, I mean a set is independent in the intersection if and only if that set is independent in every single one of our L gammoids. So now let's imagine that our set cover instance corresponds to this. So we're given a collection of elements, L gammoids, and so our sets for set cover correspond to sets that are independent in every single one of these gammoids. So now, combining the results of this paper with the results of Im et al. In 2020, what we can show is that, in fact, we can get a 2L approximation algorithm for this corresponding set cover instance. And so that is, if our set cover instance corresponds to the intersection of L gammoids, well, then we can get a 2L approximation. In fact, we can show something much more general than this. We can show that if we're given a set cover instance on the intersection of L, say, gammoids, transversal matroid, graphic matroids, or partition matroids, so that is, you give me L different matroids, where the matroids must be of the given types here, right? Then the result in our paper, combined with the results of Im et al. And Berksey et al., imply that we can get a 2L approximation for the corresponding set cover instance. So of course, here in the set cover instance, when you're given these matroids, a set is in the set cover instance if it's independent in all of these different matroids that you're given. So in my opinion, this is the main application of our work, but there's a collection of other applications that we can perform now. So for instance, if we want to do list coloring on the intersection of matroids, we can get better results using this partition reduction. Also, more generally, our results adds a lot on trying to understand the structure of gammoids. So in cases where we want to optimize over these gammoids, we have a better understanding of what their combinatorial structure is. So that's what I want to say in the talk today. Thank you very much for your time.